Hello, everyone. I have the pleasure today of talking to Nicholas Opie. He's an engineer from Australia who, together with Thomas Oxley, a physician, developed a brain-computer interface. And as I understand, you were the first to receive FDA approval for clinical trials for a permanently implanted brain-computer interface. How is it going? Is this trial already running?
Yeah, great to be here. It's going well. You are correct that we developed a novel technology to allow people to communicate just using their brain. So a lot of these patients have paralysis, so the brains work, but the transmission pathway from the brain to their limbs is not working. And so we developed a technology, like you said, a brain-computer interface that allows us to extract their intentional thoughts and allow them to control a computer just with their mind. So the trials are going really well. We completed a trial in Australia on 4 patients and are now continuing to implant participants over in the US, and so far so good. It's working really well. It's very exciting.
Great. What is it that those patients can do at this moment? Is there already the possibility to write letters on a computer or movements up, down? At what stage is a trial at this moment?
Yeah, so a lot of the patients in the US, and some of them have different conditions: spinal cord injury, stroke, motor neurone disease. These are all types of paralysis. And so we're agnostic as to the cause, but if the issue is that they can't control their ability to speech, or they can't use their hands, then they're suitable. So the patients we have at the moment are doing a range of things. They're using the computer to what's called instrumental activities of daily living, where they can do online shopping, online banking. They can send emails. They can write messages, and also we're connecting them to phones, so they can also send messages or converse with their carers. And certainly in Australia, where we've been doing a little bit longer, some of the patients are starting to interact with their smart homes, turning on their lights and their TVs and things like that. So it's very early days, but it's exciting to see just what these patients are interested in controlling, and how well they're being able to do it.
Super cool. But maybe before I continue, could you summarize how this stentrode, as you call it, how it basically functions?
Sure. So if one way to get into the brain is to perform invasive surgery, and that's where you remove some of the skull and you put electrodes directly into the brain itself. We think that that's risky and it's dangerous, and we don't want to do that. So to make sure that we can get the information out of the brain, you have to go underneath the skull, because the skull blocks a lot of the useful information. So we came up with a way by using blood vessels as a way to access all of the brain, but without doing this invasive surgery. The device we designed is called the stentrode, and to get it in the desired location, it's a procedure exactly the same as what interventionalists and cardiologists do to move around blood vessels, to remove blood clots, or to fix broken vessels and things like that. And essentially they put a wire in and a tube in, and they get it to the right location, and then they pull the wire out, and then our device is just fed through that. So it's very easy to get there, and very safe, and certainly evidence to date, only a small number of patients, but that's also confirmed that it's very safe.
Cool. So it's basically, is it the size of a regular stent that you would usually put?
It is about the size of a regular stent.
Okay. Where do you insert into the vein?
So we go to the jugular vein in the neck, and then just feed it up around, and then it sort of sits sort of right above the motor cortex. So the brain is split into different areas with different functions, and the motor cortex is responsible for intentional movement. So when you're thinking about moving your arm or your legs, part of this motor cortex becomes active. When it does, we have our sensors on the stentrode over there, and we can record it and say, the person's trying to do this now because this part of the brain's becoming more active. Let's turn that into a switch or a command that can a digital motor output to allow them to control an external piece of equipment.
Cool. So that means you train the people to think about moving their feet, your stentrode picks that signal up, and whatever the device is told to do, moving your feet means move cursor up, move cursor sideways.
Yeah, pretty much. Yeah. Yep.
What's the resolution of this? How are there several movements that you can distinguish from one stentrode?
There are, yes. The stentrodes we're putting in have 16 sensors. At the moment, though, we've taken the other approach and we've said, what can we give you with one? Let's just say we give you one. Let's see how far we can get with it. And a lot of the patients in Australia had decided that after they got one, they didn't want to learn anymore. They were happy with that, and they could do a whole lot just with that single one. And certainly, we have the opportunity now with some of the ones that are continuing to be in the trial and the new trials of trying to get more switches or more digital motor outputs and control more things.
This is very interesting that they prefer to stick to one, because I would have assumed naively that the more the better. So you can, I don't know, maybe until you get to the point where for every letter in the alphabet you have one movement, and then you just think about doing stuff. And
I think for a lot of these patients, once they get to a point where they're completely locked in, they can't move, they can't talk. For them, just reliability and being able to do it fast and accurately is sort of all they need. And doing other switches and other things, if they can write and they can do that well and with very few mistakes and at a reasonable speed, then they seem to be happy with that. And so it'll be interesting to see how it goes in the future. But it's amazing to see the benefits they can be provided with, like you're saying, with minimal resolution.
Yeah. Well, what's the current system if you want to? Maybe let's start with this. So does it have to be trained at a certain stage, or can it be used on people who are already fully paralyzed but can still receive sounds or maybe? Okay, I guess you have to be able to give consent for the whole procedure, but is there a certain stage where it's not useful anymore if you start at this point theoretically, or?
It depends on the country you're in and their management of patients with different conditions. But certainly, as long as your brain is still functioning, then it'll work, regardless of whether you can move your arms or can talk or cannot. So certainly, some of the patients in the US are now on ventilators. They're completely locked in. And they're sort of very severely paralyzed, and it's working fine with them, and they're able to converse with their physicians and carers, and tell them what they're thinking and how they're feeling at a point in time. And certainly with the Australians, that was the case as well. And some of the initial participants were on a steady decline, so we were able to see them, when they were a little bit more healthy, as well as towards the end of the journey. And again, they were able to get benefits out of it and at all time points.
Fascinating. How can I imagine this working practically if I say have one kind of signal, say foot movement, and it's click or whatever? How does writing work? Is there, I imagine, a display jumping from one letter to the next and you say stop or something in that regard? So how do you do?
Yeah, there's a couple of ways it can be done. And again, it depends on the patient. In the simplest sense, you can have a raster screen, so a screen that sort of jumps down by timing, and then you just make a click when it gets to the letter or line that you're after. When you go another level, then we've got patients who can control that rastering themselves, and have multiple different levels of activation. They can like a soft squeeze or a hard squeeze or a really strong grip. Can provide different outputs, and then you go a step further if you choose, and you can. This still is with one switch, and then if you combine it with other technologies like eye tracking, for example, then they can start moving around.
Is does it? So, sorry for interrupting. Does eye tracking stay functional in paralyzed people?
Some, not all. And so I think it's very important for us to make sure that if the patient can use eye tracking and they're getting enhanced use with the combination of an eye tracking and a BCI, perfect. A lot of the times that's not the case, and they can't use eye tracking properly, or they lose the ability to use it. And in that case, then yeah, certainly we need to make sure that the BCI can be used independently of any other technologies.
Cool.
And so obviously, once you go from just having those capabilities with one switch, or what we're calling digital motor output, then you start putting in 3 or 4. You can go up, down, left, right, full stop, brake, whatever it is that you and the technology needs. So it's only going to get better. But I'm pretty amazed by how well it's working, even at the most basic function.
Yeah, it's fascinating. I mean, I don't know anything about computer brain implants, but I always thought there must be such a huge hurdle to get something through your skull. But if you can do it via stent, I mean, stents are placed, I don't know how many thousands a day throughout the
Lots,
body.
yeah. Yeah, and so the surgery and the theaters are all there already. So clinicians don't need to learn any new tricks. It's pretty standard for them. The hospitals exist, the infrastructure, the equipment, all of that is already ready to go, and continually increasing as the number of stroke cases and other vascular procedures increases. So so that's good news. It means there'll be lots of sites available for this technology, and as well as the other technologies they're performing currently.
Yeah. And then I understand the stent rod is connected to some device that I think is implanted in the chest that is connecting via Bluetooth or Wi-Fi to any given device.
That's right. So we want to make sure that the entire system was implanted. And the reason that's important is because if you have wires sticking out of your head, then it's going to make it very difficult, and certainly not very safe if you want to use it independently and at home. So from the very start, like, this whole thing is going to be implanted. So yes, the stent connects to a telemetry unit that's in the chest that is under the skin, so it wirelessly connects to external devices, and this way the patients can leave the hospital very quickly. They can go home and use the device in their own home, which is exactly what this is about.
It's a very good point in time, I think, to develop this. As you've mentioned, smart technology. I haven't thought about connecting something to that. I was wondering whether, now with all these large language models like ChatGPT and so on coming up, maybe you can even put things very simply and just have them, I don't know, be enhanced by AI in the direction that you want. So you write 3 words and he tells you a whole sentence or something like this.
It'll be interesting to see how it goes, for sure. Yeah.
Many cool collaborations in the future, I guess. I was wondering about the training aspect. I've heard Thomas Oxley mention in his TED talk that that the parts of the motor cortex responsible for certain movements are fairly conserved throughout people. I was wondering, do you need individual training for each person to correctly enough recognize thought about right foot movement, for example?
No, I think is the short answer. More complicated than that, but I mean, we started off in our first participant. We'd go through all the different movements, hands and legs and ankles and all of that, and try and get the best signal and try and get him to use it. We've, to a large degree, stopped doing that, and we've just got the patients, it's like, yeah, you just use it, you just make it click, and that seems to be working faster and better. And so I think, we've learned a lot over the journey, and I think the decoders and algorithms to interpret the neural signals are also getting better. But certainly all the patients so far have been able to perform some click, and they've someone inherently figured out what is easier and best for them with minimal guidance, and so the training part of it is not really as necessary as we thought it was. Certainly for our technology, the device is anchored to a particular part of the brain. It doesn't move. And so we're getting the same signals all the time, and it's very reliable. I think the issues facing some of the penetrating arrays is that the brain does move a little bit, the cells move a little bit, and so what you might be getting yesterday or even this morning might not be what you're going to be recording from this afternoon. And so there's large periods of calibration required in some of these systems. that just means that if you want to turn it on and use it, that takes an extra amount of time, whereas R1 doesn't require that calibration time, just by nature of where it's positioned and the signals we're trying to record and extract.
Mhm. Could you imagine at this point, would it be suitable enough for operating a wheelchair, go forward, backward, left, right, you think?
I think that's sort of one of the next steps. There's obviously a different regulatory requirement when you're controlling physical moving things. But certainly that's one of our goals. We want to be able to connect not only to the digital environment and allow communication, but also to the physical environment. And like you're saying, control wheelchairs, exoskeletons, prosthetic limbs, all of those technologies that exist today, and certainly the ones that we don't even know about that are coming along in the future. We want to be able to interface with, and what we're trying to do is create a digital language of the brain where we can record what the person is intending to do, even if they can't vocalize it or move their limbs to act upon it, and capture this and then allow them to control and interact with their environments and loved ones. So it's not off the cards, and I'm excited. I'd love to know where it's going to go, and I think we're just going to get there for sure.
Yeah. When you say connecting to smart home, are there any specific applications or that you think about would be especially useful?
I think for a lot of these people, they've wanted to use the TV, like change channel or turn it on and off. Turn lights on and off is a big one. Some of them have been connected to the front door locks and things like that. So simple things that are relatively easy for us to do, and even some of us don't want to do them. But it's, if you're paralyzed and can't move, then having control over your physical environment too is very, very important. And that's only going to get better as more things become connected to smart homes.
Mm-hmm. Cool. How did you get this idea as an engineer? Was it Thomas Oxley approaching you as a physician, talking about stents, or did you both come up with it together? Or have you had a general interest in paralysis beforehand, or did it develop over the course of developing the stent road?
Boy, so I've always been interested in medical bionics. In a past life, I was developing a prosthetic eye, a visual implant to allow people with vision loss to just to see again, to be able to interact again, and this was a study that was done in Melbourne. So again, always been interested in the interface of microelectronics and the body, and how they can talk to each other and work together. When I met Tom back in, it was over a decade ago now, maybe 2011, 2012, he was finishing his neurology training, and I was still working on the Bionic Eye project. He had the idea of putting an electrode on a stent to get into blood vessels for paralysis, and that was certainly something that I was immediately interested in, and knew that I can make that. We can do this together, and we can make something and fill a need of the patients that just don't have any other option at the moment. So it's very exciting.
Cool. So you were mostly responsible for the sensory aspect of it, or how can I imagine this collaboration?
Originally I was sort of making them all by hand in the lab at the university. So I'd make them, and then we'd go into the lab, and Tom would try and implant them, and we'd discuss why it was good or not good and how to improve it. And then I'd go back and make another one overnight, and then we'd go in and try it again tomorrow. So it was a lot of fun, and certainly there were a lot of different iterations that we went through to get to the design that we have today.
Cool. Do you have to rely on any special material not to get too much immune function going on the electronics, or is it within a vein? Is it?
It is within a vein, and so similar to other stents, we use a material called nitinol, which is the super elastic, self-expanding nickel titanium composite, and this material is very good when a metal requires constant bending and flexing, and particularly in this case, if you want to deliver it through a very small catheter, it then expands to the size of the blood vessel, and so that was the perfect material for our device, as the the base scaffold of how we can get something in and get it the electrodes as sensors opposed to the vessel to keep the blood flowing through. And the trick was then, how do we get the electrodes embedded within this structure, and how can we get it to record the information that we need it to, and translate it and make it useful. But yeah, lots of fun.
Sounds fun. You said how many? 16 sensors it has currently? Or
currently there are 16. We don't use them all. But there are 16 on this first version.
So do I understand, the more sensors you would be able to manage and putting onto the device, the more sensible, or the smaller motor cortex changes you could measure?
It's so the more sensors you have, the more the more information you can capture. The question is whether the brain is able to deliver different information from these regions that are might not be separated by a large distance. And there's a lot of work that's going into that, to by us and other groups around the world, to try and understand what's the right amount of sensors to put in. One suggestion would be, well, we've got 10 fingers, so 10 sensors, and you can use both hands. I know there are other groups that are putting in many more for different applications, and I don't know how you'd intentionally control a device with thousands of switches. And I think that's where some of these other applications are different, because those ones are not designed for intentional control of each of these channels so much as ours. We want the person to be thinking about something, we pick it up and we do it, and they have control over the system.
But this thinking about it aspect, do you think will it be always be linked to the motor cortex, or will at some point it maybe even move away from that part of the brain, and you might think of a ladder, or is the resolution, or theoretically
nothing's off the cards, right?
Central of the future.
Yeah, nothing's off the cards. I mean, there's certainly there's blood vessels everywhere in the head, and there's a lot of regions we can get to, both for people with paralysis as well as other neurological conditions. You see people at the moment are getting knitting needle style electrodes pushed down into the middle of the brain to help them with Parkinson's tremor or epilepsy. We can get to those regions. It's just a matter of can we get the signals we need to record when a seizure is happening, and can we do stimulation to prevent the seizure from occurring? I don't see why not, but that's sort of a future question.
Was that what was meant with two-way communication, which I've read on the homepage of the EPO? So you can design them in a way that you can send signals in a way that stimulate a certain brain region, or theoretically.
You can. Yeah. So groups are doing this already. So like Parkinson's disease, for example, you send electricity in, and that will interact with a part of the brain and stop the tremor from occurring.
Is this already part of the trials?
No, not ours. This is other brain technology. So I think to your point, where can the Stentrode go, and what can it do? The future's very broad and very exciting, and there's a lot it's going to be able to be used for.
Cool. I imagine so. Last question: when would you assume a possible commercial launch?
Hopefully next couple of years. So we're finishing off at the moment our clinical trial in the US, and it was called an early feasibility study. That then gets turned into a pivotal trial, and the successful completion of that pivotal trial is when you get approval to commercialize the device. You get market approval to commercialize. So that's not going to be too far away. And certainly we're very excited about the current progress of the technology. We haven't had any device-related adverse events, so there's been no risks to the patient so far. In that regard, all the patients have been able to use the technology. So far everything's looking great, and we can only hope that it keeps going that way, and it gets out to the people that need it really soon.
Great. crossing fingers. Hey, that was super interesting. Thanks,
Yeah.
Nick, for your time.
Yeah, no worries. Thank you.